I mean, I guess yeah. So, anyways, hello, my name is Nathan Cho, but I guess everybody refers to me as Nacho because it's a very convenient nickname. And I'm here to talk about this method called cheesing with this presentation that I and I guess a friend and a helper, Shirag, wrote. And if you have any questions during the presentation, you can private message him, and he should be able to answer your questions. So I guess without further ado, let's get into it. So many of you guys might not really, well, many of you guys might know what cheesing is, or maybe you don't know what cheesing is, and maybe you guys don't really see how cheese really applies in math, but I guess, well, that's what I'm here to talk about today. And cheesing is, it's a, it's a specific method that we use um, that applies to certain math problems in competitive math. And ultimately, the idea is that um, we're going to be making these choices in the beginning in order to make our lives much easier throughout the computation and the rest of the solving of a certain problem. And usually this involves problems that um, might not necessarily have a singular configuration, but the answer applies to every single possible configuration. And that's sort of what the case of cheesing is. For example, if we consider any parallelogram, we know that there are many parallelograms, and some of them can have different angles from each other. And um, in the case of, for instance, being given a parallelogram, if there are no conditions that are imposed onto it, we will be able to just assume it's a rectangle in some certain circumstances. So maybe what I said doesn't make any sense. So let's actually look at an example. And this is from the AMC 10 2001. It's a problem 3, so it's one of the first few problems of the test. And well, let's read the problem first. And so the problem says the sum of two numbers is s. Suppose 3 is added to each number, and then each of the resulting numbers is doubled. What is the sum of the final two numbers? Now, this problem doesn't seem like a very difficult one, but let's just see what it has to say. So, of course, all the answer choices we can see are in terms of s. So, without loss of generality, if I choose 1 and 99 as my two numbers, then their sum will be 100, right? So then I can just do my operations on 1 and 99 and add 3 to both of them, and then double both of the resulting numbers. And then basically I'll get an answer of 212. And so if my initial sum was 100, then my answer is now 212. That's the same as 2s plus 12, so our answer is E. But this brings about another question because, well, just as easily, I could have just said, if I have the sum of both numbers as s, then I add 3 to each of them. It's the same as adding 3 twice and then doubling this. And I'll just get 2s plus 12. So I can just do this all algebraically instead of having to do um, this intermediate addition and, I guess, computation. So, well, why the heck would we choose 1 or 99 in the first place? And even though this is an instance of cheesing, it's a really bad one. And you'll see later that there are much better instances of cheesing, but this is just a problem that we can use to sort of get the idea of what this assumption-based cheesing is. So here is a more, I guess, applicable problem to this. And this is a problem from, I think it's either the Nismol or the Armel. So anyways, the problem reads, in triangle ABC, AB is equal to AC, and D and E are on AB and AC respectively, such that BD is equal to DE and DE is perpendicular to AC. Compute the measure of EBC. Now, looking at this problem straight on, from the conditions, we can, I guess, tell instantly that ABC is isosceles by definition, and now we have to construct these points D and E on AB and AC with these further given conditions. Now, if we notice, these conditions with D and E aren't very restrictive on, I guess, the placement of A. We can have, for example, AB it can be shorter than another configuration. Like for example, I can have this. Like I'll just draw one example first. Say this is my triangle ABC. Then I have, well, I have D on AB such that BD is equal to DE and DE is perpendicular to AC. So if I were to guess, it would look something like that. Where, well, I guess probably something like this, where I guess this is D and this is E. But I guess in the same sense, I could also draw a triangle that looks like this, which looks completely different. And I guess I could still have the same conditions. Actually, probably not for this obtuse isosceles triangle, but still, you get the point. I can draw a completely different isosceles triangle that looks like this, for example. And it would like, my diagram would look like this, where I have D here and E here. And, well, if they're asking for this angle EBC, we notice that there are infinitely many ways I can have the ratio of, say, the side lengths AB to BC. But if they want a numerical answer, then, well, that means this number has to stay the same within all configurations. And this is the concept of cheesing. So we can see that, as I said earlier, A can be placed anywhere as long as we have that ABC is isosceles.
不是，
Yikes. Let me get this person muted. Okay, anyways,
这个一个，
yikes. How to mute people. Anyways, so if EBC is staying the same, well, we can try to maybe come up with a way to find EBC in a really easy way without having to do a lot of intermediate steps. And this comes from the following assumption. So right now I will show you a cheesy solution. So as I did earlier, I drew these like several diagrams. Well, I guess two to be precise. But as we notice, all these are isosceles triangles, so all of these satisfy the conditions, and it's just about where D and E are. Now, I'm going to make a really wild assumption. I'm going to say, what if I make AB like extremely long? I'm going to make AB like the longest segment you've ever seen. In fact, it'll be the longest segment you've never seen because it's going to be so long that it's going to go like off the screen. And then, well, eventually these 2 points are going to meet somewhere. Make this isosceles triangle. But for now, we get these lines that get closer and closer to parallel as A gets farther and farther away. And so then our conditions, well, if you notice, BD equals DE, so BD equals DE will look something like this. And then we have this perpendicularity. So if this is equal to this is a perpendicular. Well, we can see this is getting closer and closer to a square. So like, if this triangle were infinitely long, then these lines would basically parallel, and then we would have this square pretty much. Because, well, nothing in the problem said I couldn't have AB as an infinitely long segment, and there are no conditions in the problem which make it so that I can't choose these segments to be infinitely long. And then when I make them infinitely long, I basically get a square. So then if I compute this angle, it's obviously going to be 45 degrees because it's half of 90 degrees. Like 90 degrees over 2 is obviously 45 degrees. So this is the answer to our problem. And this is basically what cheesing is. Like we ask ourselves, what am I allowed to do with this problem? Is there going to be only one configuration? Like, for example, if somebody tells me I have a triangle with like the side lengths 3, 4, and 5, then this triangle is predetermined. And we say that there are no degrees of freedom. In other words, there are no other possible diagrams I can make. But if, for example, in this problem, they only give me that it's isosceles, I can still put A wherever I want. And this is, I guess, the main point that has to be clear here. So let's go on to another example, or I guess more about cheese. So here are the benefits of cheesing problems rather than solving them conventionally. Well, first of all, it can be really fast. For example, in the previous solution, if I just cut out all the explanation that I did, I could probably solve it in like maybe less than 15 seconds. Just think for 10 seconds. Well, what if the lines are basically parallel to the triangle? And then another 5 seconds to just think it'll become a square. And then my answer is 45 degrees. Also, there's a lot less work. I didn't really have to do any intermediate computation. I didn't have to do any intermediate steps. All I did for that specific example was, well, I just assumed something, and I knew that my assumptions were within the scope of the problem, which ultimately let me get to an answer really quickly and really efficiently. So this brings us to the question, well, why wouldn't we choose a problem if it's really going to be easier, faster? And, well, of course, there's a slide for this too. So it should be known that not every problem can be done with cheese. Like, as I said earlier, if we have a predetermined diagram, it's not like you can assume a certain length if they give you the length, or if you cannot possibly draw a triangle with those possible, like those certain lengths. So you always have to think about where you have freedom to assume stuff in the problem, where it'll be, I guess, legal in a sense. Furthermore, well, sometimes a cheating solution can be not as motivated, so you might not see the steps as clearly as you would see with another problem, for example. And also, if you make the wrong assumptions in the beginning, then you're probably going to get the wrong answer. This is a true fact. If you assume that a certain segment is like 200 when it's when it certainly says in the problem statement that it's 150, then you're going to get the answer wrong, unless you're extremely lucky. But you don't want to put your bets on that. And also, if you find out in the end that your cheating solution didn't really bring you to a certain point, well, you just wasted a lot of time. And if this were, for example, on the AMC 10, then, well, you would lose a lot of time. And in certain competitions like the AMC 10, time is all that matters. But furthermore, let's talk a bit more about cheesing, because honestly, cheesing is just really fun since it makes everything easy. Let's consider this problem AMC 10B 20. It's problem number 20 from the 2002. I know this is a huge gap from 3 to 20, but throughout this lecture, I'm going to be continually increasing the difficulty of these problems because cheesing is actually a technique that we can use on an extremely wide difficulty range, just not many problems inside the difficulty range. So let's read the problem. So let a, b, and c be real numbers such that a minus 7b plus 8c is equal to 4, and 8a plus 4b minus c is equal to 7. Then a squared minus b squared plus c squared is, and then we have 5 options. So, well, something that we can first notice when we're looking at this is that we're given the conditions on the, I guess the numbers a, b, and c are that they have to satisfy these two linear equations in a, b, and c. So the system is in 3 variables, but our condition is only in 2 equations, which means that, well, if you know, I guess, linear algebra, or if you just think about it, if you try to solve for any variable a, b, or c, you will not be able to get an exact value. You'll get an answer that is in terms of the other 2 variables. This is because when we have a system of 3 linear equations, we will have to have, when we have a system with 3 variables, we will need at least 3 linear equations. So that means that there isn't going to
Yeah.
be only,
Okay.
there isn't going to be only one ordered pair, or ordered triple, I should say, that satisfies the conditions given. So I guess this is what makes us think about a chasing solution in the first place. Because of this very loose condition on A, B, and C, when I say loose, I mean like not predetermined. This means that we can make assumptions freely, and I guess we should be able to get a numerical answer from this. So I'm going to do this right now. So, well, if a minus, I'm going to write this out. So a minus 7b plus 8c is equal to 4, and 8a plus 4b minus c, oh god, I can't write, plus 4b minus c is equal to 7. As I said earlier, it'll be very difficult to solve for the value of a single variable in this case, because of the fact that we only have 2 linear equations and we have 3 variables. So in other words, if we have a certain ordered pair that satisfies, let's say x, y, and z satisfy, we will also be able to find another ordered pair like p, q, r that also satisfies a system of equations, and these two ordered triples being distinct. So that's why I'm going to do the following. I'm just going to assume that A is 1 because I know it has to be true for all ordered triples. So let's say A is 1. If A equals 1, then we have now the equations 1 minus 7b plus 8c equals 4. And then we have 8 plus 4b minus c equals 7. And so what we get from these equations is that minus 7b plus 8c is equal to 3, and then 4b minus c is equal to negative 1. Now, we can just do like some classic solving equations. So I guess one approach we could do is multiplying the second equation by 8, getting 32b minus 8c equals negative 8, adding it to the first, and we get 25b equals negative 5. And then so in this case, we will get b is equal to negative 1/5. And then we could just plug in these now into the equation. So if I plug in, for example, negative 1/5 and 1 for a and negative 1/5 for b into, say, the second equation, I would have 8 minus 4 over 5 minus c equals 7. And what this means is that we're going to have 1 minus 4/5 minus c equals 0, which means that 1/5 is equal to c. And did I do? Yeah, so then what we get in this case is that 1 squared minus 1/5 squared plus, well, I guess this should be negative 1/5 squared plus 1/5 squared. And we see that these terms cancel out because of this minus and plus. And so then our answer is just 1, which we got just by assuming that a is equal to 1 and finding a solution that satisfies. So I guess that's the cheese for the AMC 10. So I guess we're going to, take a small time to, make some clarification since all this in the beginning
Mm.
can be pretty confusing. So does anybody have like any questions about what I've talked about so far? What time will the class end? Um, the class will end, I would say probably around 9. Jerry asks, I'm assuming you can't choose proof problems, and that's where you're wrong. I'm going to prove I'm going to prove an ISL problem at the end with a cheese flavored solution, not necessarily a perfect cheese, but it's going to be a roughly cheese flavored. Is there any other questions? I can answer any other questions, I guess. Nasha, why are you big brain? I'm not. I'm just a guy who does math. Anything else? Why is it called cheesing? Um, Honestly, I am not the person who came up with the name, but cheesing, I guess, was a term that has been in existence for a while inside of the competitive math community. Who came up with the name? I have no idea. What inspired me to pursue cheesing? Well, when I got this offer to lecture, I wanted to find a topic that would be applicable to an extremely large audience. And so I guess cheesing just came up as one of these topics that I knew I could teach that also, I guess, worked out. Does cheesing in place other than math? I'm
No,
not
what
sure.
I mean is, does choosing take place um in areas other than math?
I mean, if you make a, if, I mean, I guess in a way, cheesing is over glorified guess and check in some sense. It's just that you know that your guess is always going to be checkable. Let's see. Um, what kind of problems can be cheesed? So this is well, okay, the answer is all types of problems, but not every problem. Yes, Harry is right in that cheesing can be applied in any question that has extra degrees of freedom. And what we mean by extra degrees of freedom is that we have um, we don't have a predetermined diagram. For example, if like I said earlier, if I give you all three side lengths to a triangle, then that determines the triangle. There's no multiple triangles that have those exact three side lengths. But for example, if I had instead just a line, like if I told you this side length and I told you this angle, then I could have, for example, this triangle, I could have this triangle, I could have this triangle, and these would all satisfy. And this is where we have an extra degree of freedom. Um, so I guess it's really important to know when these degrees of freedom apply. And you can check these just by, for example, trying to draw another diagram. Um, how do people come up with these creative solutions? Well, I guess one thing that is really important to know about cheesing, it's not just something that comes out of nowhere. It's not something that like comes out of a magic hat and poof, it's cheese. It's more of it's more of there's a motivation that comes from, well, if I think about this, how does the problem hold true when I modify it a bit? So, for example, in the Armo question I showed, the one about the isosceles triangle, that was, I guess, one of the first instances where I thought about cheesing, and I was mocking the Armo test for my club, and then I just well like I didn't really like geometry. I still don't really like geometry. So what I did is I asked myself, what can I do instead of trying to chase random angles? What can I do instead of finding the value of each of these individual angles and then trying to get this one angle? And I reached a solution where I basically thought, what if this triangle basically became like the bottom half of a rectangle? And that's where I got my answer from. And so that's, I guess, where I first learned about this technique. Um, Anyways, if those are all the questions, I guess, let's keep going. And now we're gonna up it a bit, and we're gonna go to the HMMT. So this is the HMMT February. Oh, by the way, just an aside, I personally enjoy uh, considering cheesing as a verb. I don't really like. I like to think about cheesing the problem, not like really a cheese solution. So let's talk about this HMMT February 2017 problem. So, well, just to be clear, this contest is not an easy contest. So it's not like this problem is going to be easy with a limited amount of knowledge. Oh God, there's more questions. Oh no. Does cheesing work in combo problems? Sometimes it does. It really depends. Like sometimes when somebody writes a problem, there's going to be exactly one way that the problem is configured. But in another sense, you could also have a problem where it's very loose. So like these conditions can be changed, but the answer will stay the same as long as there's a certain condition imposed. So then in that case, you can just take out one condition that is extraneous. In other words, a condition that has no, it doesn't really serve any purpose in the problem because the answer stays the same. And in that case, you have a problem that's cheesable because you're able to make these certain assumptions that make your life really easy. Anyways, let's go back to this HMT problem. So if we have ABCD is a convex quadrilateral with AB equals 5, BC equals 6, CD equals 7, and DA equals 8, and we find the midpoints of all these sides, then what will this answer be? This mn squared minus pq squared. So one thing that we can consider, earlier when I was talking about these predetermined triangles having all their side lengths, the same doesn't really apply to quadrilaterals because quadrilaterals, I guess, they require more structure in order to be predetermined. For example, in the case of a square, if I said all the side lengths are the same, then I could also draw a rhombus. And this would also be an instance of a quadrilateral where all the side lengths are the same. Similarly, if I said, well, what if I defined a square as a quadrilateral all of whose angles are 90 degrees? Then I could also draw a rectangle, and this would also satisfy. So, in other words, these quadrilaterals can't be easily predetermined. And in this case, they just give us these four side lengths. So we'll basically be able to like squish it if we want. So like basically squish it so that it looks more like this or like whatever. there's going to be more than one quadrilateral with these exact side lengths. So, um, well, so yeah, as I said, these quadrilaterals aren't uniquely determined only by the side lengths. We would also need like angles in order to make it a singular quadrilateral, which means, well, this HMMT is a computational competition, so there's going to be a numerical answer. So this makes us quite suspicious. This answer is going to stay the same no matter what I do, no matter which quadrilateral I choose. And another thing that we can notice is that these side lengths are actually in an arithmetic progression. And this is actually going to inspire a really nice chasing solution in this case. So, well, if I have a side with side length 5 and then with 6, well, these differ by 1. So like the difference of like if I drew this, it's going to be a difference of 1. Same with the side lengths C and D. Their difference is also going to be 1. So what if I made this problem a lot easier in this case? What if I drew the quadrilateral? Well, I'm going to use coordinates in this case because it's harder to express this without using coordinates. So let's consider the point A at 0, 0. And since AB is going to be equal to 5, I'm going to say, let's make it 5, 0. And then C is going to be at negative 1, 0, because that's 6 away from B. And then D is going to be at negative 8, 0, because it has to be 7 away from C. Now we see that the distance from A to D is actually 8, which is the same as what they give us in the problem. Which means we just made a line equal to a quadrilateral. And I mean, this should honestly seem like cheating because we're literally turning a quadrilateral into a line and then computing the answer from that. And, well, some people might think about this in a different sense. They might say, well, the problem says convex. And is this quadrilateral necessarily convex? And I can assure you that this can fall under the definition of convex. Because if I consider, like, for example, let's consider this quadrilateral. And I say, well, I'm going to draw these 4 points. If this is 180 degrees, it'll just degenerate into a triangle, which is a convex shape. So, I mean, it shouldn't matter if we have several 180 degrees, as long as none of them are greater than 180 degrees. So, basically, now all we have to do is see, okay, M is going to be equal to the midpoint of side AB, which is 2.50. N is going to be equal to the midpoint of CD, which is going to be negative 4.50. And then we have P is going to be midpoint of BC, which is going to be 3, 0. And then Q is going to be at the point, which is the midpoint of AD, which is negative 4, 0. Then, well, obviously the distance from M to N is going to be 7. And then the distance from P to Q is also going to be 7. And so we see that we can just square this, subtract, and we get 0. And like, that's our answer. We're done. Yes, this should seem like sorcery because we're literally turning a quadrilateral into a line. But this is the beauty of chasing. We're taking these non-trivial problems and we're making them easy because, well, I guess in a two-dimensional system, it's hard to find the distance between these midpoints. A note that we can have is that if we wanted to solve this without chasing, without assuming that it's a line, we could use, I guess, some methods using vectors, but that gets a lot more bashy than this does. This is literally like, what, a two-line solution, defining the points and then computing this distance, which is why you should see how powerful cheese is. So now we're going to jump a bit farther, and we're going to look at 2012 Amy 1, problem 14. So this is one of the last 5 problems, which are known to be extremely difficult. So let's read this problem. Excuse me? Oh, okay then. So this, well, at a first glance, it's not purely geometrical, which might be slightly concerning, knowing that basically all the problems we've cheesed so far were geometrical. But cheese can be applied to basically every single subject, just more often in geometry. So complex numbers a, b, and c are zeros of a polynomial p of z is equal to z cubed plus qz plus r, and magnitude of a squared plus the magnitude of b squared plus the magnitude of c squared is equal to 250. The points corresponding to a, b, and c in the complex plane are the vertices of a right triangle with hypotenuse h. Find h squared. So, yeah, that's a good observation, Skylar. But first, let's look at this. When we consider a concept that most of us should know pretty well, Vieta's formulas, then we can see that there is no z-squared coefficient. And, well, we know that the coefficient of the z-squared term is going to be equal to the sum of the roots. Or I guess we could say the 0. So this implies that we have a plus b plus c is equal to 0. Now, notice how q and r have literally no context in this problem. Like, we're just given that q and r are numbers, but we're not told to find q, find r, find anything involving q and r. Just something involving the zeros. So this should make us quite suspicious, but for us, we're going to think of it as a blessing because this is going to make our lives easier in making our assumptions. So at our first glance, we see that q and r don't have any restrictions. They just need to be numbers. And the only restriction in this case is the z-squared coefficient, and also the fact that the magnitudes of a, b, and c is equal to 250. So, I mean, we should have enough time. This is an Amy 14. Assuming that you got this far, you either have very little time left and you're just trying to guess a random answer, or you're solving it for the first time, but you also notice the same things that we have here because these are the only restraints. So without further ado, let's just chase the problem, okay? So let's say, well, we know a plus b plus c is going to be the same as 250. So, well, sorry, a plus b plus c is equal to 0. So without loss of generality, I'm just going to make, let's call it a 2x. And you'll see why in a second. Then I can define b as, well, it's going to be a complex number. Or we're going to hope it's a complex number. So then we're going to have minus x plus yi. And let's make c minus x minus yi. So in this case, we have all the roots summed to 0, which is desired. But if we think about this in the complex plane, it's going to look something like this. So let's assume that just for the sake of this, x is going to be on the left side of the complex plane. So we're going to have it something like this. And we have our b is going to be something like here. C is going to be something like that. So we get this isosceles triangle. And, well, we want this to be a right triangle. So a really obvious choice that we could have is we're going to make it a 45, 45, 90 triangle. So instead of this, we're going to make it instead, let's make it instead this triangle. So it's going to look like this. So this is going to be a right angle. And this is a 45, 45, 90 triangle because it's isosceles and it's a right triangle. So now all we have to do is, well, since this is a 45, 45, 90 triangle, we can divide it into two. So like, I guess the real axis does that for us. And now we get two smaller 45, 45, 90 triangles, like the one right here. So if we're given that this is this small, the short length, I'm going to make this a bigger diagram because it's nice to have something bigger. So let's draw this again. It's going to look like that, or this is a right angle. That does not look right. But anyways, so this length is going to be 2x. This is going to be x, and this is going to be y, because, I mean, this is the real part, and this is the imaginary part. And so we can see that this length sums to 3x. But this triangle is a 45, 45, 90 triangle, which means that y is equal to 3x because this is isosceles. So now that we have y is equal to 3x, all we need to do is use this condition, and then we can find exactly what x is and exactly what y is, which makes our life extremely easy. So now we can just substitute 3x for y, and then we get this is equal to negative x plus 3xi, and then this is equal to negative x minus 3xi. Notice that the magnitude of b and c are identical, and these magnitudes are going to be equal to x squared plus 9x squared. Well, I'm sorry, I'm considering the magnitude squared because we're going to be having to deal with the magnitude squared anyways. So these both become 9x squared plus x squared. And then for a, we get 4x squared. So then if we sum these all up, we're going to get 24x squared is equal to the sum of the magnitudes. And we know this is equal to 250 because that's the problem statement. So then we just have x squared is equal to 250 over 24. Now, looking ahead, I'm not going to take the square root of this to find x because I can use something else. Recall that our right triangle looks something like this. And we knew that this was y. And so that means our hypotenuse is equal to 2y. And y is equal to 3x. So then that means our hypotenuse is equal to 6x. Now 6x squared, because we're trying to find the length squared, is equal to 36x squared. So that means we just need to multiply this by 36. And then we'll get our answer basically instantly. We get our answer is equal to 375 just by doing some computation. And this is quite, well, this is quite a cheese because as you can see, it literally destroys this AMY 14 into maybe a 2-minute solve, maybe even less. Because all we're using, like notice, all we're using this solution is a simple assumption that A is real. We just assume that A has no imaginary part. And then what we were able to do from there is create these assumptions that basically led up to us having a 45, 45, 90 triangle. And then it was just a matter of simple geometry to come up with our answer. And I guess this is something that we should know for all problems that are cheesable, I guess. These problems, even though they are cheesable, we need to remember that cheese is not necessarily a 100% winning game. We have to remember that there's high risk involved, and it's high risk but high profit situation. If you cheese it, you could either get the answer really quickly, save a lot of time. If you don't, then you lose points and you waste time. So even though like these select problems that I found are very cheesable and very nice, it's not always going to be the case. So you should never use cheese as your primary method of solving a problem. And furthermore, if you do cheese a problem, it's always a good idea to check your answer at the end, if you have the time, of course. And after the competition, to solve it without a cheese method completely, just for a learning experience. Cheese is a purely competition technique, but not necessarily, I guess, formal math technique, because it does involve exploiting the fact that we're looking for a computational answer in many of the cases. Now let's look at, I guess, I think this might be the final problem. And, well, it's an Olympiad problem, so it's a proof problem. And, well, those aren't cheesable, right? But it turns out that you can still use a cheesing idea. So like the idea of cheesing can be sort of applied to proof problems as well, depending on the problem, of course. So without further ado, let's read the problem. So this is from the International Math Olympiad shortlist. It also was the Ukraine TST problem in problem 10. So let's let b and n be greater than 1 and integers. Suppose that for every k greater than 1, there exists an integer a sub k such that b minus a sub k to the nth power is divisible by k. Prove that b is equal to a to the nth power for some integer a. Now this can be a lot to digest at first. So, well, I guess some things that we could look at is that the only thing that we're trying to show in this case is that b is restricted to being a perfect nth power solely by the condition on all k greater than 1 dividing this term. And since all values of k work for this, we know that, well, our k are going to be looking like 2, 3, 4, 5, and so on. But we know that like 2 and 3, they don't share any common divisors. 3 and 4, those are completely different. One is 2 squared, the other is a prime number. And this goes on forever. It's not like we can characterize a certain group of numbers as the same necessarily just by, well, for all k, that's going to be pretty difficult to characterize all k in the situation. So there is a purely number theoretical solution to this using the maximum number of times a prime number divides the expression. But we're going to use a cheesing flavor solution. So notice that we must have, for the sake of brevity, I'm going to replace AK with A because, I mean, writing the entire K is just way too much work for me. So well, we know that if B is equal to A to the nth power, then for all K, we can find a number such that K divides this because we can just define K is equal to A minus B. Sorry, this should be lowercase a. Oops, I am bad. That's not the eraser, darn. Okay, so we're going to replace, so we know that K has to divide this. If we say K is equal to big A minus small a, then we know that this is always true because of a simple result in, I guess, modular arithmetic. And if you don't know this, it's just that A is congruent to A mod A minus A. Oh, that's not where I put the mod, oops. And in other words, the remainder of A is the same as lowercase a when I divide it by big A minus small a. And then I can put both sides to the nth power and get that the remainder of A to the nth minus A to the nth is equal to 0 when divided by big A minus small a. And this basically gives me that this always is true. So that means that if B is equal to big A minus small a to the, well, big A to the nth minus small a to the nth, then we can always find this K. In fact, we can construct the value of K such that it divides. The problem here is that we need to prove that B is equal to A to the nth. So that means, well, first of all, if we know that K divides B minus A to the nth power, what we can do here is we can say, just like we did earlier, that this must be true. And what this does for me personally, this inspires me to choose a certain modulus that'll make my life really easy. And in this case, since I'm looking to restrict this perfect nth power condition, I'm not going to choose B, but choosing something related to B is a good idea. Because if I just make it B, then the left side is going to be equal to 0, and it becomes sort of obvious. But if I decide instead to make the modulus b squared, so because b squared is greater than k, we know that this must be true for b squared. Then we get b squared is congruent to a to the nth power. Now, what this means is that, well, for a to the nth to be equal to b, we need a to the nth to be, well, congruent to b modulo b squared. Then we would need a to the nth to be in the form b times bx plus 1. Because if it were just in the term bx, that for some integer x, then this x would just be sent. We could just choose b because if x were b, then it would be b squared, and then, well, modulo b, that's not gonna get us anywhere. So we're trying to force this term a to the nth to be congruent to b modulo b squared. So not divisible by any power of b, only b. So in other words, we have automatically forced that no b to the nth can divide a. Well, no b to the nth can divide a to the nth because of this modulus. Now, this is basically where the sole motivation comes from for choosing b squared. It makes it possible to remove any exponent on a number greater than 1. So then, if a to the nth is congruent to b times bx plus 1, then we can see that this is obviously true. Because expanding, we get b squared x plus b. B squared cancels out in the modulus, and then it's just left congruent to b. So we can say, in order for this to be true, a to the nth must be equal to b times bx plus 1 for some integer x. Now, furthermore, we know that a to the nth is congruent to b times bx plus 1 mod b squared. Which means, well, actually, I can change this condition, sorry, to equal to, because that has to be true in order for this to work in this statement. And then, well, if a to the nth is a perfect nth power, then obviously this has to be a perfect nth power because it's equal to the perfect nth power. But the problem here is that we can see obviously that the GCD of b and bx plus 1 is equal to 1 because, well, we can just subtract b constantly from this side, otherwise known as the Euclidean algorithm, and then we see that b does not divide this, and no prime divisors can actually divide this term. Well, no prime divisors of b can divide this term, so therefore the GCD is equal to 1. Now, since they have no common divisors at this point, we know that both of these terms have to be perfect nth powers because there's no way that we can combine divisors of b and bx plus 1 to become a perfect nth power because of the fact that they share no common divisors in the first place. So therefore, b must be a perfect nth power. And so this basically finishes our solution. So if I were to basically write this in a time-conserving manner, I would just do it in the following way. I would say, um, since since k is greater than b squared, sorry, that is completely wrong. I meant that the other way around. So since b squared is greater than k, we can choose b squared, well, is greater than 1, sorry. Then we can choose b squared as k. Then we know that b squared has to divide b minus ak to the nth power, which implies that b is congruent to a to the k, a sub k to the nth mod b squared. From this point, we can instantly notice that the left-hand side is equal to b plus b squared x for some integer x, which becomes the
这就是
factorization
对的，
b
那写的 n
becomes
号，
bx plus 1. Now, since the GCD, so the greatest common divisor of b and bx plus 1 is equal to 1, we can instantly tell that they have no common divisors. Therefore, the common divisors cannot group together in order to become a perfect nth power. Instead, we have b is a perfect nth power and bx plus 1 is a perfect nth power. And since b is a perfect nth power, we are done because this basically completes the proof. And that's an international shortlist problem solved using a cheesing idea. Instead of proving this for all k greater than 1, we proved it for 1k and showed that this forces us to have b as a perfect nth power. Any questions on that? I mean, this is sort of the end of the presentation. We went a bit quicker than I anticipated, but basically this is cheese. This is basically the concept of cheese, where, as I've demonstrated throughout, I guess, this 50 minutes, cheese is very powerful in the fact that we can just make our lives easier based on our own accord. So are there any questions for any of the previous problems I did, or I guess cheesing in general, or questions at all? Can I explain how cheesing will help you in future potential future mathematics careers? Well, it can, I guess this question could be interpreted as a joke, but actually this is a very reasonable question. And so the concept of cheesing means that we have to be able to apply a certain situation for every situation. In other words, we're choosing a specific subcase out of a large group of cases. And for research mathematics, choosing these small cases can be really helpful because using these intermediate cases can ultimately help you to develop the intuition needed in order to prove it for the bigger case. So in other words, like for example, even in like a lesser context, and like for example, the Olympiad setting, if I'm looking at a geometry problem that wants me to prove something, then I can modify my diagram a bit, and I could try to make observations based off of that. Even though that's not necessarily cheesing in itself, cheesing this idea of taking this specific subcase and then analyzing it to make observations is going to help because a lot of the times these things that stay true for maybe 3 diagrams is going to stay true for all diagrams with certain conditions. Does that answer your question? All right, glad to hear it. Anything else? Cheesing demonstrates high IQ. Well, not necessarily. Cheesing is, I guess it's one of the most intuitive methods that can ever come up. It's basically the equivalent of guess and check. I like to think. Like it's basically guess and check in the sense that we're guessing, but in the case that we're guessing, we're not guessing an answer. We're guessing a certain condition that must be satisfied. And a lot of the times, this condition that must be satisfied is very, very loose. And yeah, basically professional guess and check. Well, something that somebody wanted me to mention is that cheesing is definitely not going to be the relied on method. That's why I think, in my opinion, that's why cheesing isn't necessarily taught. It's more intuitively done, and it's used as maybe a last resort method. In the case of a competition, we would use cheesing as a way to get an answer when we don't have one already, or maybe as a way to establish an answer and then check that answer using conventional methods. But um, so, like, I guess in the sense, it should be not necessarily your first go-to method, because if you try to cheese every single problem in existence, you'll either be extremely successful and I'll be amazed and I'll be very, very amazed, or you're going to maybe probably just fail. And um, yeah, I've been asked to say that cheesing is very high risk, high reward, because you're not necessarily always going to get an answer from cheesing. But if you do cheese it in the right way, so making the right ideas, coming up with the right cases, then you're going to get profit from that. You're going to get like 10 points on the Amy, or an additional 4.5. Thank you, Shirag. Yes, it's very important that you think it's a high risk, high reward situation. Otherwise, David Alexia is going to kill me. No, I'm kidding. Brendan Jiang says the professional theory of choosing a relative simplistic solution. Yes, that is exactly the idea. Can choosing help improving inequalities? Um, I mean, whenever you think about, well, for the specific case of proving inequalities, you always have to find an equality case. And in the case of equality cases, it's those are usually stuff that you can instantly see at first. But chasing also helps you know how tight an inequality is. In other words, how close like one side of the inequality is to the other. Can you say my name? No, I'm not going to. Um, yeah, so Harry, we can say cheating is directly related to meta solving, because cheesing is basically a technique where we're reverse engineering the competition itself. It's 100% exploiting the fact that we have a numerical answer in most of the cases, and this is what leads us to say, why does this answer stay the same for all degrees of freedom, for all diagrams possible, for all specific scenarios? For example, let's think back to that the AMC 10 problem from earlier. This one. So we can see that we're trying to find a squared minus b squared plus c squared, and we know that this has to be numerical, and that's why we can instantly think of a cheesing solution. Does cheesing have anything to do with fake solving? So I think that cheese is 100% legitimate in the fact that if you cheese correctly, you get the right answer. Fake solving is more of you make an assumption and it's wrong. Um, and in that case, that's a fake solve, because you make an assumption, or you build up reasoning that is completely false, and then from that point you either get the right answer by accident or you get the wrong answer because your reasoning was wrong. Chasing is a scenario where you think about it and you say this must be true in order for there to be an answer. If you want to learn how to legit solve this, how would you legit solve this? That is a very good observation. Let's see. For this problem, you can just cancel out like I guess, one of the variables. But so I guess the main observation to make in this AMC10 problem is that, well, a squared minus b squared plus c squared can must be able to be derived from the linear equations. So I guess from that point, it's just a matter of making the right manipulations. Yeah, assuming spiral similarity on AME13 is not cheesing. That's guessing, and that's not checking. That's just guessing. And like meanwhile, cheese is subtle, very very subtle assumptions. You can't assume a triangle similar to another, but you can assume a side length. Like, for example, in a lot of the cases, we'll see a more simple example where we're given a side length and then we're given a configuration in geometry. And in that case, we can just scale everything down so that maybe our side length is equal to 1 and then solve the question at that point. And then you can scale it back up. Um, do you want to advertise CNCM? Okay. You have one message to do so. All right, that's your one message. Any other questions? Oh, by the way, the solution for the ISL problem that's legitimate involves taking it's basically taking the p-adic valuation. So like I guess most people don't know the terminology, like the VP of the K that divides into this expression. And from there, that basically leads us to leads us to an inequality that must be strict only when B is a perfect nth power. If there's no other questions, then I guess we're basically done. So thank you for coming. I hope you learned something from this lecture. Is there a handout associated with this lecture? Yes, there is, coming out very soon. It's basically the same as the presentation, but it'll have basically nicely typed out solutions and it'll be in proper paper form. So I guess that's particularly thanks to Chirag for basically reformatting this entire lecture into that. So I guess that's it for today. I guess we stopped exactly at 1 hour, and thank you for coming again. I hope you did learn something. Maybe it was just how to solve a certain problem, or maybe the entire concept of choosing itself, or maybe the motivation behind choosing. So I bid you all good luck in your future mathematic endeavors. Goodbye.